Right, so in this module, we're just going to consider a simple example in which we're going to try to find the Fourier series expansion of the simple periodic signal sine omega naught t. Now, there are two methods of doing it. One of them through the Hydrous expansion directly, which just gives you the direct synthesis expression. And the other way we're going to do it, just for clarification of concepts, is through the analysis equation as well. So the first way is just by using the Hydrous expansion. X of t is sine omega naught t, and I know that the Euler expansion of sine omega naught t is 1 upon 2j e raised to power j omega naught t minus 1 upon 2j e raised to power minus j omega naught t. And if you just look at this expression by itself, this is of the form of the Fourier series expansion. So if you recall, the Fourier series expansion is of the form x of t equals k going from minus infinity to plus infinity, ak e raised to power j k omega naught t. And if I compare this expression with what I have over here, I can immediately see that all of the Fourier series coefficients in this are 0, except those corresponding to k equals plus 1 here and k equals minus 1 here, right? So this is the term corresponding to k equals plus 1, and this is the term corresponding to k equals minus 1. And as a result, my solution is that the Fourier series coefficient A1 is equal to 1 upon 2j, and the Fourier series coefficient A minus 1 is minus 1 upon 2j, and all other Fourier series coefficients except these two are equal to 0. So that's directly through Euler's expansion. For clarification of concepts, let me also use the analysis equation to try to determine the Fourier series coefficient. And of course, the results that we obtain from that should turn out to be the same as with method 1. So for method 2, I'm just going to use, as I said, the analysis equation directly, which, if you recall, says that the Fourier series coefficients ak are given as 1 upon t integral over 1 period t, the signal x of t times e raised to power minus j k omega naught t dt. And plugging in x of t as being equal to sine omega naught t over here, what I get is 1 upon t. For this particular example, this is sine omega naught t e raised to power minus j k omega naught t dt. And what I can do next is just to use Hydrous expansion once again. So 1 upon t integral over 1 time period t. And this is 1 upon 2j e raised to power j omega naught t minus 1 upon 2j e raised to power minus j omega naught t. So this is the sine signal times e raised to power minus j k omega naught t dt. And what I need to do next is just to evaluate this integral. Let me just separate them out into 2. So this is 1 upon, so let me take the 1 upon 2j out, and then this is 1 upon t integral to t e raised to power j omega naught t times e raised to power minus j k omega naught t times dt. And then there's the next term, which is minus 1 upon 2j, and then 1 upon t integral from e raised to power minus j omega naught t times e raised to power minus j k omega naught t times dt. And all I need to do is to evaluate these two integrals separately. So this is 1 upon 2j, 1 upon t integral over 1 period. This is e raised to power j 1 minus k omega naught t dt minus 1 upon 2j 1 upon t integral t e raised to power minus j 1 plus k omega naught t dt. And if you recall from our discussions in the previous module, I know what this integral is. I know that this integral is going to be equal to 0 whenever 1 minus k, whenever 1 minus k is not equal to 0, and is going to be equal to 1 because it's 1 upon t. This is going to be equal to 1 whenever k equals 1. So my conclusion based on our discussions in the previous module is that this integral is going to be equal to 1 whenever k equals 1 and is equal to 0 when k is not equal to 1. Similarly, as far as this integral is concerned, this is going to be equal to 1 only when 1 plus k equals 0, which implies 1 plus k equals 0, which implies that k equals minus 1 and is 0 whenever k is not equal to minus 1, right? So based on these results, what I can conclude is that ak, which is this thing over here, is going to be equal to 1 upon 2j whenever k is equal to plus 1. So whenever k equals plus 1, I know for a fact that this integral is going to turn out to be equal to 1, and this integral is going to be equal to 0, right? Similarly, when k equals minus 1, when k equals minus 1, this is going to be equal to 1 upon minus 1 upon 2j when k equals minus 1, right? So, and the reason for that, of course, is that when k equals minus 1, this thing is going to be equal to, this integral is going to be equal to 1, and this is going to be equal to 0. And for all other values of k, which are either not plus 1 or minus 1, not only is this 0, but also this is 0 as well. And therefore, the sum is also going to be 0. And our conclusion, therefore, is that ak equals 1 upon 2j when k equals plus 1, ak equals minus 1 upon 2j when k equals minus 1, and is 0 otherwise. So 0 otherwise. And that's our conclusion. And this is exactly the same result that we had earlier.